Okay, well, good evening. The Montgomery Amateur Radio Club here in Maryland is proud to present Al, KN3U, to talk to us about intermodulation interference. Al is president of the Montgomery County Auxiliary Communication Service and a fellow MARC member. Thank you, Al, for joining us tonight to share your expert insights on a very important topic. So over to you.
Okay, so I guess, can I get a quick audio check while I share a screen here?
Your audio is fine, Al.
Okay, great. I'll try not to shout then. It's good evening, everyone. And here's the slide where I show that I know what day it is today, and we'll move right along. Well, let's see, what do I have to click? There we go. MARC has recently been experiencing some interference with its 2-meter repeater that results in conversations on Montgomery County government channel being retransmitted by our repeater. And a couple of months ago, there was a fair amount of speculation about why this was going on the repeater and on the reflector. And it's actually a textbook example of a well-known phenomenon in two-way radio. It's known as intermodulation interference. So I thought that club members might be interested in learning a little bit more about this topic. I called Alex or dropped her a note and she said, sure. So that's how I came to be talking to you tonight. I wanted to just put the bottom line up front that I'm not currently a member of the MARC Repeater Committee, although we do help each other out from time to time. Many of you also know our another MARC member, Ross WA2WDT. He and I have operated a 220 megahertz repeater in Rockville for over 30 years. And I have supported or overseen a number of amateur radio and government repeater installations over that long period of time. And in the course of that work, I've been on rooftops from Boston to Miami and some places out further west, and often working with really experts in the field. And I've learned a whole lot from those experts, but I am by no means an expert myself. So make that clear up front. And I also want to say that tonight I'm speaking as a club member and an interested party, but I'm not speaking on behalf of the repeater committee. I've had a couple of conversations with Fred, who's the repeater trustee, about this interference. And I can assure you that Fred and the committee are well aware of what the problem is. They have a lot of information about it, and they understand what's going on. As I'm going to explain to you presently, knowing what the problem is and finding out how to fix it are two very different things. So we'll get into that here in a few minutes. Okay, so I want to start by talking about, not about the MARC interference issue, but another one that I encountered several years ago, which is, again, is kind of a textbook case study. So this is a good place to get started. This is an incident of interference. It's now in the past, so we know the end of the story. And so we'll start here, and then briefly at the end, we'll come back to talking about the situation here at home. Okay, so back in September of 2013, it's almost 9 years ago, wow. I received a phone call from a friend who manufactures commercial grade weather radios. And he is well connected with the National Weather Service. He was deeply involved with the development of the NOAA weather radio system and the protocols that they use to broadcast warnings. And from one of his many contacts in the weather world, he had learned that the NOAA weather radio station in Manhattan was interfering with the reception at a Coast Guard facility on Long Island. And more precisely, the weather radio broadcasts were being heard on Marine Channel 16 at a nearby Coast Guard facility. And many of you know that Channel 16 is a distress channel. the Coast Guard was really concerned that this interference could cause them to miss a distress call and lead to real harm. And they were insisting that the weather radio station be shut down. And at the time that I began to hear about this, the problem had been going on for about 2 months. So my friend was corresponding with a number of folks from different agencies and a few people from private companies who are trying to solve this problem. And he, kind of brought me into this loop and put me on the email thread. And some basic facts had been gathered, not all of which turned out to be correct. But no one on the email thread seemed to have a clear idea how or why this was happening. And a number of people assumed that there was something wrong with the NOAA transmitter and that it just needed to be shut down until it could be fixed, which was not actually the case. At that time, the transmitter, the weather station, was located on the top of a skyscraper in Midtown Manhattan, within a block of Grand Central Station. And the Coast Guard receiver was on top of a waterfront high-rise condo directly across the East River, the blue spot you see on the map, about a mile away from the transmitter. And it was remotely operated from a Coast Guard facility at some other location. I actually never knew where the Coast Guard facility was. Here you see the MetLife building looming over what we used to call Grand Central Station. Now apparently they changed the name, it's Grand Central Terminal, okay? On the right, you see this tall, skinny tower that was the location of the Coast Guard radio that was being interfered with. And as you can see, it's right on the water, and there's presumably a clear line of sight between these two buildings. Now, at the transmitting site, there were tons of radios on the roof, including a VHF repeater operated by a law enforcement agency. And by the time I got involved, someone had already determined that the interference on the Coast Guard channel only occurred when this government repeater was keyed up. And of course, the NOAA station was transmitting continuously. So that's kind of the extent of what was known when I got involved. So I asked for and received the frequencies of the NOAA station and the government repeater. And you see them on this chart here. And so I, very simply, suspecting that this was a case of intermodulation interference, I did a very quick calculation to see if that might be the case. And I had this booklet published in 1972, which is many people consider to be the Bible of intermodulation interference. And I looked around on the website, on the web, and I couldn't find a copy of it anywhere. There are lots of people referring to it, but I couldn't find a PDF of this document. So I scanned it myself. I have a photocopy of a photocopy of a photocopy, as you can see from all the hole marks on the left side. And I scanned it and I sent it off to this group of people that my friend had gathered together. And then I did a little bit of simple arithmetic. There we go. So I took the second harmonic of the NOAA weather radio station, 162.55 times 2 is 325.1. I subtracted from that the frequency of this repeater, the output frequency, 168.3, and bingo, the result was exactly the center of the Coast Guard Channel 16. You think that's a coincidence? I don't think so. All right, so now I know that I also did the kind of the complementary calculation, and I multiplied the frequency of the government repeater by 2 and subtracted it from the NOAA weather radio frequency, and I got the frequency of 174.05. So based on doing those two calculations and knowing a little bit about intermodulation interference, I can be pretty sure that if someone was to go up to the roof of that city lights tower on the right and tune their radio to 174.05, they would hear the broadcast on that frequency as well. So, okay. So what, why did I do these two particular computations? Well, because I read that book that I just showed you the cover of, which isn't actually a book. It's about 15 pages long. So to answer that question of what's going on here, I have to digress momentarily. And while I'm digressing, I have to tell you that I used to hate it when my professors would say that. Well, we've got to digress. But in order to understand intermodulation interference, you've got to understand the concept of mixers in RF circuitry. So in modern communications gear, we often want to translate an RF frequency to a higher or lower frequency. And we use a circuit called a mixer to do that. Here is a block diagram of the receiver in the FT991. And I know that some members of the club have this radio. I kind of picked it out at random, but if I'd have picked out almost any other radio, we'd see a similar kind of diagram. So there are no less than 5 mixers in this receiver, 3 of which are used on HF in 50 and 6 meters, and a couple others that are used on the VHF and UHF bands, 2 meters and 440. So not to belabor this anyway, but let's say we're listening at 7.2 megahertz on the 40 meter band. So there's a 7.2 megahertz frequency or signal coming into the receiver and going through the attenuator circuit, going through a 40 meter bandpass circuit and a little bit of amplification. And then it goes into this circle with a X in it that's really designed, it's intended to show a 4 quadrant, a circuit with 4 connections, only 3 of which are being used here. But in any case, also fed into that circuit is the output of an oscillator. And the purpose of the mixer is to produce signals at the sums and difference, is to replicate what's coming in at the sums and differences of those input frequencies. And in this case, well, let me just stop there. We don't need to get a whole lot into more detail about that. We're not talking about HF radios today. We're talking about mixers. So what is a mixer? Well, when you have a linear circuit, like an op amp configured as an amplifier or a filter, the output signal may have more or less amplitude than the input signal at different frequencies, but there are no frequencies in the output that weren't already present in the input. So if you have, 2 frequencies coming in, you're going to have 2 frequencies coming out if you have a linear circuit. There may be more or less of those signals if you're trying to filter one and emphasize one and de-emphasize the other, but you're not going to generate signals at a different frequency. When you have a nonlinear circuit, if there are 2 things happen. If you have 2 signals, if you have just one RF signal at the input, you get the harmonics of that signal at the output. So that's 2 times the frequency, 3 times, 4 times, so on. And in addition, if you have more than one frequency coming into a mixer, then at the output, you also have the sums and differences of those 2 input frequencies. And so then you can use a filter circuit to pick out the frequency that you want. And I'll show you an example of that in a minute. But so how do you make a mixer circuit? Well, if you want a nonlinear circuit, the easiest way to do that is to put a diode in the circuit somewhere that does the rectification, because a rectified sine wave is about as nonlinear as you can get with one component. So when you rectify a sine wave, you get lots and lots of harmonics. And if you put more than one frequency into this diode circuit at the same time, you get the sums and differences of all those frequencies at the output. So a diode is a really good way to make a mixer. And I can assure you that in the FT991 receiver, each one of those mixers has at least one diode and sometimes several involved. There's some tricks you can do with the way you configure the diodes to get more of what you do want at the output and less of what you don't want. But the key is that anytime you have a nonlinear circuit, and especially a rectified waveform, you have some in different frequencies and you have harmonics. Okay, so let's keep that in mind. And now let's get back up to the rooftop, the main story. So here's a rooftop that is near and dear to my heart. So my question to you is, do you see any rust here? And I've seen worse, but there's a fair amount. And anytime you have two dissimilar metals in contact with one another, you have a diode, you have a rectifier circuit. It's a law of physics, maybe it's even in the chemistry textbooks, that when you have dissimilar materials in contact with another, there's a contact potential that's generated, and the signal flowing from one material to the other is not symmetrical with any current flowing in the opposite direction. So anytime you have corroded materials or a rusty bolt at a repeater site or a receiver site, you have a mixer circuit. So where is this mixer circuit getting its input from? Well, a rusty bolt is a conductor, which means it can be an antenna. So if there's a nearby transmitter radiating, by the way, let me just give you a little hint. The antenna on the far right there is the WM3M-10 RMS gateway. So this particular rooftop is not too far from home. I don't know what half of the rest of the stuff up here is. Some of it's government stuff. That dish in the middle of the picture is a Mapen microwave dish. That's one that I know about. Let me see if I can get my cursor up here. This thing here is a piece of hardware that used to hold a cellular antenna hanging over the roof. And they've long since, that was like the first generation of cellular equipment. The antenna's long gone, but the junk is still laying there 20 years later. It's been sitting up there for 20 years. There's another, I don't know if you can see it, there's a bolt laying on the roof right there. There are cables here that are no longer in use, and they were not removed when the equipment they were connected to was taken away. In another part of this roof, there's a whole microwave dish with a big box attached to the back of it, and the wires are hanging off the box. It's sitting there. It hasn't been used. Maybe it was left in place as a hot backup for something that replaced it. But in any case, there's all of this hardware up there and electronic stuff that is absolutely chock full of metals in contact with one another, that if there's any current induced in any of those metallic bits, there's going to be rectification occurring, which means that you're going to have sums and difference frequencies being generated and harmonics. And it just happens that sometimes the signal that's generated at a different frequency is strong enough that it gets re-radiated by that piece of metal, and it can cause interference with someone else's radio. That's what intermodulation interference is. And this is if you see this much rust and this many opportunities, there's dozens of them here, are opportunities for this kind of mixing to appear and to produce an interfering signal on a completely different frequency. And notice that what I'm talking about happening here, the transmitter that causes this interference can be working perfectly the way it's designed to work. The mixing and the re-radiation of this interfering signal is occurring in a piece of junk that's just laying on the roof. Clearly not the responsibility of the transmitter owner to fix a problem like that. But it is a problem for the receiver that's being interfered with, right? And the biggest problem is understanding, figuring out which piece of rusty metal up here is the one that's causing the interference. So you can understand what, what's happening theoretically or from a math model or, or a circuit model, and still, we're not very close to solving the problem, are we? Because how do we find out which rusty bolt is the one that's radiating the signal? So in the case of this NOAA weather radio incident up in Manhattan, we were very fortunate that somebody figured out early on that this government repeater was the other frequency involved. So we knew what the two frequencies were. So I created a little spreadsheet after I got involved in this thing. And this is, it's fine print. Since you're at home on Zoom, maybe you can see the numbers. But basically what I've done, I've called the two transmitters that were involved in this incident, frequency A and frequency B. And let me see if I can get my cursor up to the left there. There you see frequency A was the government repeater. Frequency B was a NOAA weather radio transmitter. And over on this side of the spreadsheet, I listed all combinations of sums and differences of those two frequencies. So A plus B, B minus A, and A minus B. And then this mixing can also occur between harmonics of those frequencies. So I took frequency A and added it to the second harmonic of frequency B, and a frequency A minus the second harmonic of frequency B. And now you can see what's going all the way down here. So I did this all the way up to the third harmonic of both transmitters. And I end up with a long list of frequencies that could all be produced by this rusty bolt mixing just from these two transmitted frequencies. And so that I did this calculation just to show the people that were trying to solve this problem what they were dealing with. But in this case, or in many cases, what you're really trying to figure out is this problem. You know the radio that's being interfered with, in this case, the US Coast Guard Marine Channel 16, and you know one of the transmitters, but what if you didn't know what the other transmitter was? So what I did was take the original calculation and solve for frequency A. So I just turned the equation back around, and now if I know what the victim frequency is and I know what frequency B is, frequency A could be any one of these. So a transmitter on any one of these frequencies in the results column could be causing the interference that was being experienced on Marine Channel 16. And you notice that half of these frequencies are negative. So we can cross those off the list right away because I've never yet seen a transmitter that transmits on a negative frequency. But the ones that are positive frequencies, any one of those could be a viable source. And you can see that here near the top of the list actually was what turned out to be the actual offending transmitter. Again, there's nothing wrong with this transmitter, but there's a rusty bolt somewhere or a rusty connection or a corroded coaxial connector on a piece of coax that's laying on the roof that's causing the problem. But it's really helpful to know where the transmitters are located. So once I have this, I now only have a short list of frequencies where I can look around and see where there's a transmitter nearby. And a lot of these frequencies are not likely to have a transmitter on a rooftop in Manhattan, but there's a few of them here that might. So anyway, this kind of a calculation is really useful for narrowing your search down. And once I have this list of frequencies, I can actually go to the FCC database, which has a search engine, and you can type in a zip code and a frequency, and you can see if there's any transmitters in the FCC database that are licensed to use that frequency. And very often you'll get a direct hit. And you, instead of searching for a specific frequency, you can search over a range of frequencies so that even if it's close but not right on the money, you'll still catch it if it's in the FCC database. And there's a similar database for transmitters that are managed under the federal government's licensing system, which is separate from the FCC. So, these are tools that you have when you're trying to find the source of an intermodulation problem. Okay, so so now, we know what's going on. How do we find the rusty bolt? It could be near one of the transmitters. It could be near one of the receiver or the receiver that's being interfered with. So what are some things that we can do? So the first step in troubleshooting a problem like this is to go to the location of the receiver that's being interfered with. And that receiver, people who do this for a living call that the receiver the victim. The intermodulation could actually be occurring within that receiver's antenna hardware, within their feed line. If there's any inline filters in that, and a corroded or rusty connection anywhere in any of that hardware on the receiver front end, even inside the receiver's front end circuitry, those are all places where the intermodulation can be occurring. So the problem might be right there at the receiver site, but not necessarily. It could be on the building. It could be on this building over here that the intermodulation is occurring. If there's any rusty gutters, rusty balconies, any of those things could be causing the problem. Now, when you're listening to this interference, you can often hear voices that give you a clue about the offending transmitter's identity. In this case, the NOAA weather radio broadcasts were being being heard very clearly on Marine Channel 16. So they knew the identity of that transmitter right away. And you can go up on the roof where the receiver is and tune a different receiver to the same frequency and use a direction antenna and see what direction the interfering signal is coming from. Again, it might be coming from across the river. It might be coming from the building next door. It might be coming from a piece of hardware 10, 20, or 30 feet away on the rooftop. You can also go up there with a spectrum analyzer and look for blips on the spectrum analyzer. If you don't know what the other transmitter's frequency is, you can look for blips on the spectrum analyzer that coincide with when you can hear the interference. And then once you know what the frequency of that signal is, then you can go looking for where it's located. So there are tools you can use. Once you know the frequencies of the offended transmitters, you can find out where they are, go to those sites and see if the interference is stronger at the transmitter site than at the receiver site, which gives you an idea that you need to be looking for a rusty bolt in that area instead. I'm sorry, where was I? I scrolled in the wrong window here, sorry. I think really the key point of this is that figuring out why the intermodulation is occurring and then figuring out where it's happening, where the rusty bolt is, that's the hard part. So just to make a long story short, from what I, at some point in this incident back in 2013, some real experts got involved up in New York City. They were a lot closer to the problem that they were, and they a lot more knowledgeable than I were. So I bowed out and let them handle it. And later on, after the fact, I learned that the experts never did definitively identify the source of the interference. Even with the best minds in the business, they had some really good people working on it because I actually talked to some of them. They never did figure it out. The NOAA radio station was off the air for an extended period, except for when they were running tests at low power. The Weather Service eventually decided to move the NOAA transmitter to a new location, and they ran tests at several different locations around Manhattan to try and find a good location that wouldn't have an interference issue. Eventually, they picked a site, and then negotiations with the building owner fell through, and they couldn't come to agreements on a contract. And so they had to start over again at a different site. And the bottom line was the station was not back on the air at full strength until 2019, 6 years after the problem occurred. Wow. So, and that's with some really smart people working on the issue. Okay, so you know, early on in this process, as I was trying to explain to the people who were involved at that point, I asked a series of questions. You know, what changed? Why did this start in July of 2013? Was there any new installation of equipment? Were there modifications to the building? Was there modifications on the roof of either of these buildings on the upper floors? What's the precise description of how the interference manifests? What's it sound like? It turns out that if the interference is caused by a harmonic of a transmitter, when the harmonic is generated, the deviation of the signal doubles. So if you have 5 megahertz deviation, 5 kilohertz deviation, like the NOAA weather radios do, and you take the second harmonic, the signal there has 10 kilohertz of deviation. Then when it gets mixed to a third frequency, it still has 10 kilohertz of deviation. So you're trying to listen to this interference with a 5 kilohertz receiver, but you're listening to a 10 kilohertz deviation signal. It sounds loud, twice as loud, or twice the amplitude, and it sounds very distorted because your 5 kilohertz radio can't even keep up with such a wide deviation. So if you're dealing with the intermodulation interference and you hear a loud distorted voice, chances are, it's almost certain actually that you're dealing with a harmonic rather than the fundamental frequency. So there's all kinds of tricks that you can use to figure out, where it's coming from. You can ask if the interference varies with the weather, time of day, or any other observable pattern. Does it appear to be completely random, or is it intermittent? And all of those answers to those questions give you clues as to where the interference is coming from. But again, you have to find the rusty bolt to fix the problem. and that's really hard. So just to bring this home, this is my last slide. The experience that we're experiencing on the Mark repeater right now, we're fortunate enough that we're able to hear the voice of one of the offending transmitters, and we know that it's a radio used by the ride-on system in Montgomery County. We've never quite figured out what the other offending transmitter is, and it's not necessarily just 2 signals being mixed, it could be 3 or 4. So it's really, but the good news is that Montgomery County has a new communication system that's all the county government equipment or users are being switched over to this new system, which is really, it's more of a cellular design than it is an old-fashioned VHF, UHF radio design. So right now, the county is installing new radios in all the ride-on vehicles. And in just really just a couple of months, they're gonna move over to this new radio system. And the transmitter that's causing our interference on the Mark II meter repeater is going to be decommissioned. And so we're no longer going to have an intermod problem. And chances are that transmitter is going to go away long before we find the rusty bolt. So that's my story. I hope that was informative, and I'll open it up to questions, and back to net control.
Wow. Well, thank you, Al. That was terrific. So Fred has his hand up. Go ahead, Fred. Oh,
Yeah.
Al, could you take down your screen share?
Oh, sure.
Yeah, thank you.
Yeah, so first of all, I'd like to thank Al because yes, he and I did work together. I gave him some of the frequencies. I gave him the frequency that I thought may be being interfered with. So he, was able to do the reverse calculation that knew the interfered with frequency, and we knew the ride-on frequency because actually we could hear the ID and everything on that one. And actually I confirmed it with the county and was able to listen to that frequency. But it is true that it had to be an intermod or some other sort of thing, because not every time that they were transmitting did I hear the information coming out on the mark repeater. And it's really strange that some days it was really bad. It would go on almost all day long. And then other days it might skip a couple of days, then it might come back again. And again, that makes you wonder about the weather or, some other things that have possibly changed. The other thing I thought was really interesting that I did not know until Al mentioned this time was about the deviation. Because I always wondered why, when they are coming through the mark repeater, the audio level sounds pretty much consistent with what we have. And we normally have like 3.5 to 5 kilohertz deviation. But since they're in the commercial land mobile service, their deviation is half of that, and their bandwidth is half of that. But now that I understand that if it was a harmonic that was being involved and that got doubled, then that's why it would sound kind of consistent with ours in terms of the audio level. So I thought that was interesting that I didn't know before. Lately, it seems like it's gone again. I haven't heard it for, at least the last several days. So I'm not sure. I'll check with the guy that I know at the county and see if he knows if they maybe that. Well, no, I know it's not off the air because I listen to that frequency and I still hear them talking. So it hasn't gone away, but whatever the cause is, either the bolt dried up, somebody went up on the roof and kicked it and it's somewhere else now, or, like you said, and the other thing too is like the heat, the cold, things expand. If it's right at a joint somewhere between the bolt and the mast it's attached to, then, that's going to change things too. So it's very interesting, but I appreciate all of Al's help and helping at least me understand what the problem was. Unfortunately, like he said, we still haven't found the either the other frequency or what might be. Even if we knew the other frequency, we still don't know what is causing the mixing to occur. So the other thing too, I just wanted to mention too, that just because I noticed it on your presentation when you were listing the things, and it sort of immediately came to my mind as soon as you mentioned that it was a Grand Central Terminal, is I think actually one of the frequencies that's on your spreadsheet actually is a railroad frequency, because the railroads use the frequencies in the 160 range too. So, and I thought I saw one of those was on there that just happened to be. So again, it could be different frequencies at different times of day or whatever. So thanks.
Great. Okay. Bob has a question.
Thank you. Al, thank you very much. That was really informative. I had two questions. Could we, by any chance, get a copy of the article, the AT&T article? I searched the web for it, and I found reference to it, but I couldn't find a copy of it. And secondly, is there a governing, I don't know how to say this, but is there a governing body of law? Is somebody acknowledged as being responsible, or is this just the Wild West as far as it's your problem because it's bothering you? Thank you.
Good question. So I actually meant to say this, since I couldn't find this on the web, and I don't know what the legal ownership might be. But if anyone sends me an email, I'll be happy to email you my scan of my photocopy of a photocopy. So KN3U at ARRL.networks. And I'll be happy to share. It's actually, as it was written in 1972, those were slide rule days. I didn't even have a calculator until 1974. I couldn't afford one. In those days, the cellular system didn't exist and mobile telephones were in use and they were in a certain part of the VHF band at channels that were like 15 kilohertz or 25 kilohertz apart. And on the rooftops in Manhattan, they had rows of these transmitters and antennas lined up, feet apart, and on very closely spaced regular frequencies, which is kind of a first place for intermodulation interference to be generated. It's a factory for intermod. So it was a really big issue for the Bell system. So they spent a lot of time trying to figure out how to make transmitters and receivers and antennas that wouldn't have rusty bolts, so that they wouldn't have this problem. And that's why they wrote this manual. And the manual was published in 1972, but their literature on intermodulation interference goes back 30 years before that. So this is a very old problem. And now what was your second question, Bob?
Is there a governing body of law on this issue?
Right.
Who's responsible?
Right. So nobody regulates rusty bolts. So if it's your receiver that's being interfered with, it's your problem to solve. And most transmitter operators, if it's their transmitter who's involved, the first thing they have to do is make sure that the rusty bolt isn't in their transmitter system, because then it is their problem, right? But that's really easy to determine with a test receiver. If you get up close to your transmitter antenna with a receiver, and you're not hearing the interference there, then it's got to be coming from somewhere else. So it's the receiver owner's problem to solve the problem. But, transmitter operators will generally try to help.
Okay. Dave?
Just a quick thought. I know this is probably not the recommended solution, but could you create a small low power transmitter installed near your repeater transmitter that actually shifts the intermod frequency away from something that'll cause interference? I realize that could add to somebody else's problem, but is that even a possibility?
Theoretically, I would say, yeah, that's a possibility. I think it would be really hard to implement in practice. And in a lot of cases, I think the signal levels would not be constant. If we're talking about a rusty bolt transmitter, it's got those two input frequencies. It's going to be producing that interference. When you're asking a question, I'm almost thinking about, could you put a transmitter near the receiver site to null it out, opposite phase to cancel it? I think that would be really hard to do too. No, you really do have to. You have to use some direction finding techniques to find it, and theoretically, it should always be possible to do that. But in the jungles of the rooftops of a big city, for an intermittent signal, that is a really tough direction finding problem. And these signals are not very big. All it takes is a microvolt of signal at the antenna to have almost a full quieting FM signal. So you're looking for very, very tiny signals in a jungle.
Okay. Are there any more questions? All right. Well, Al, thank you.
I have a comment. Sorry.
Yes.
That's actually on the extra class material about intermod. I recognize that 2 times the frequency minus or plus or minus the other frequency. So for what that's worth, so anyway, that's all.
Okay. Well, great. All right. Are there any more comments? Okay. Well, Al, thank you for a terrific presentation. As always, you give such great information and you are such a wealth of knowledge. So we really appreciate you taking the time to be with us. And thank you to everybody that viewed in to our Zoom session. And 73 to all.
All right.